RLIs in the galaxy.
How do I advance this?
Oh, gosh, this one. I think it's this one.
And this is the,
Laser, yeah.
okay. So I guess I will. Put the mouse over here. All right. Hi, so my name is Andrea Kunder, and I'm excited to talk to you today about the BRAVA RR Lyrae survey, which is a spectroscopic survey of RR Lyrae stars in the inner galaxy. And I first want to thank George for having this birthday party and giving us an excuse to all get together and talking about our favorite stars, RR Lyrae stars. So thank you for choosing that star. And it's been really a wonderful conference so far. So I wanted to start by reminding everyone what the bulge is, the inner galaxy, shown right here. This is a zoom in of the inner galaxy from the Blanco-Deckham bulge survey, which Mike is going to be talking about later on today. And you can hopefully see from this picture that the bulge is only maybe the most daring astronomers will probe, thanks to its gas and dust clouds that obscure the view. And also it's very crowded. And so source detection and blending is a real issue. But the galactic bulge is not an insignificant component, weighing in at about 20 billion solar masses. And so the questions are, how was the bulge formed and how does it fit into our understanding of the evolution and formation of the Milky Way galaxy? When we look at the bulge, there are two main observations that are important to its understanding. One is the shape of the bulge is flattened and elliptical. So this is a surface brightness contour map in the 2 micron wavelength of light of the bulge. And you can see that the bulge is not round. Instead, it looks like a basketball has been flattened. And you might be able to see on these positive longitudes, it is not very symmetric with the negative longitudes, and it's more poofier, more broadened here. And that is because our bulge is actually a bar. These stars are closer to us than these stars. And so what we are looking at is the bulge is a thick bar that's inclined along our line of sight. So here's our sun. These stars are closer to us than these stars. The second important observation about the bulge is that it is rotating in a cylindrical manner. We saw this by the BRAVA survey, which Mike was the PI of. And this plot shows that at positive longitudes, the bulge stars are primarily moving away from us, whereas at negative longitudes, the bulge stars are primarily moving toward us. So the bulge is going toward and away from us, toward and away from us. And we know it's rotating cylindrically because when we measured their radial velocities as a function of latitude, we saw that there is really no change in mean velocity as a function of latitude. If the bulge was rotating like a sphere, we would expect stars right along the plane of the galaxy would be moving faster. And as you move further from the plane of the galaxy, they would be moving slower. But we just don't see that. We see similar radial velocities at different latitude bins. So instead, the bulge is rotating more like a cylinder. And from these observations, we can fit a model to the bulge, suggesting that the bulge was formed from the disk. So here is a simulation put together by our group where the Milky Way galaxy starts as a disk, and there's some perturbation and it begins to buckle. And over 3 or 4 giga years, the disk evolves in such a way that the central component becomes poofy, poofs out, becomes like a boxy peanut-like structure. And importantly, our n-body models show that the radial velocities of the stars resulting from such a formation mechanism agree exactly, very similar to the radial velocities that we have obtained. Since our BRAVA survey, there have been other spectroscopic surveys of giants and red clump stars in the bulge, and they all agree with our BRAVA results. The bulge is rotating cylindrically, and the best interpretation for these observations is that the bulge formed from the disk. The competing scenario of how the bulge formed was that the bulge formed from mergers of 2 galaxies, likely when the universe was much younger and when it was smaller and hotter. So here's a simulation of 2 galaxies coming together. When they merge, they'll form a more massive galaxy with a bulge that is round and has stars on random orbits. So bulges that form from the disk tend to be boxy. We call them pseudobulges. Bulges that form from a merger tend to be round and have stars on random orbits. However, there are intricacies in this kind of simple interpretation. For example, pseudobulges can also have a round component if there were stars in the disk with different initial velocity dispersions. The stars with the largest initial velocity dispersions could still form something that is spherical. And with a classical bulge, you could get a classical bulge that looks more elongated like a bar, because the bar could spin up such a classical bulge, causing it to actually take on a bar-like appearance. So it's not always so easy to interpret the observations from the inner galaxy, but we will try. So within the 11 megaparsec sphere, massive galaxies such as our own Milky Way galaxy, which is also a massive galaxy, they tend to either have pseudobulges, so boxy bulges, or no detectable bulge. And this is a little bizarre because we all believe in lambda CDM, and so we expect that there should be lots of mergers that occurred, and so there should be quite a few also round classical bulges that are apparent, and we just don't see that. And so one explanation for this is that bulges could be bimodal in nature. So there's a pseudobulge that dominates the light that we see, but embedded in the pseudobulge could be a fainter, classical bulge that that is, less visible to us. So our bulge is the closest bulge of any other galaxy, and so we can use our bulge as a test bed to see, is there really a bimodal bulge in our Milky Way galaxy, and could this also be then possibly also be the case for the other massive galaxies that we see in our vicinity. There have been some suggestions that our bulge is bimodal. This is a plot from the Gibbs survey. In the Gibbs survey, they used VLT to take metallicity and radial velocities of stars in these fields. And here are the metallicity distribution for those stars. And what the Gibbs survey did is they separated the stars in the bulge by metallicity. Those that have supersolar metallicity from 0 to 0.5, they call metal rich. And those that have subsolar metallicity from 0 to -5, they call metal poor. And they had to do a grid of interpolation because see, their fields are not, they're pretty spread out, the fields. But if you interpolate the data, they found that the most metal rich stars look like a pseudo bulge, a boxy kind of bulge, and the more metal poor stars look more spherical, kind of more like a classical bulge. So potentially there are these two bulge components. In the Blanco-Deccan bulge survey that Mike is going to talk about, we have increased, this was based on 5,000 stars. Now we have 2.5 million red clump stars with abundances, photometric abundances and distances. And we also can confirm the most metal rich stars look like they are part of kind of a boxy pseudo bulge. The most metal poor stars look like they are more spherical in nature. And we don't have to do any kind of grid or interpolation. We can just plot, number density of stars in the sky. So there's something there. So how about the Aurora stars, our favorite stars, the reason why we're here today? Well, George Preston found in 1993 that the Aurora stars in Body's window are, maybe more metal rich than in the outer parts of the galaxy, but still -1, -1.2, still more metal poor than most of the bulge stars that have been probed. This is a histogram that shows the metallicity distribution from the red clump. This is like 2.5 million stars from BDBS paper. And this shows the metallicity distribution of the Aurora stars. This is a spectroscopic Aurora distribution from Savino et al. 2020. And so the question is, well, what do these old metal poor stars in the center of the galaxy show? Could there be a classical bulge component, or in this more metal poor regime? Remember, the other stars kind of went down to -1. We're now probing a different space in FEORH. So let's first talk about what the spatial distribution of the Aurora stars show. Do they look more spherical or do they look more boxy? So 20 years ago, this is a debate that goes back, 20 years ago. So the answer is we still don't really know. So 20 years ago, there was the Macho and the Ogle survey. We heard about the Ogle survey, and we heard that George was also involved with the Ogle survey when it first began in Ogle 1. And so, 20 years ago, using about 3,000 Aurora stars in the bulge, the Macho survey found that the red giant stars trace this bar that's inclined, brighter, here and fainter here, but the bulge aurolari stars don't seem to trace the bar. It seems like they are, don't have any kind of slope in them, suggesting they could be a more round spheroidal population. However, the OGLE-1 group finds the aurolari stars do trace out the bar. So immediately there's this controversy here. 10 years later, we have OGLE with 20,000 aurolari stars, still finding that there is an elongated distribution of stars in the bulge. And then the VVV survey, which is detecting aurolari stars in the longer wavelengths of light, used the OGLE aurolari stars and plotted their spatial distributions here. And the black points are the aurolari stars, and the red line are the red clump stars. So the red clump stars show this barred feature. You see, these are brighter, these are fainter, whereas the aurolari stars don't seem to show a barred distribution. So we still have a discrepancy in the literature. And just this year, a paper came out. The VVACE has now 50,000 aurolari stars. They went through the VVV database and picked up aurolari stars also along the plane of the galaxy. So here are the aurolari stars that were published by Molnar et al. In 2022. And what they found is they found that the aurolari stars do seem to trace out a bar distribution. And to find these distances, they used Wessenheit reddenings. This are the same aurolari stars, exactly the same here, but instead of using Wessenheit magnitudes for reddenings, we use reddening maps from the VVV, in particular Julia Simeon's reddening map, which has 1 arc-minute by 1 arc-minute resolution. And you see, depending on what reddening you use, you get a different spatial distribution of the aurolari stars. So I would say we still don't know exactly what the spatial distribution of the aurolari stars. This reddening in the bulge is extreme, and I would be curious for people in this audience what they think about using Wessenheit magnitudes versus the typical reddening maps that are derived from from stellar populations. Yeah, so here you see the sloped line, and here you see a very minor slope. So more kind of, like hardly a slope at all. So if you say, what is the, are the aurolari stars brighter on one side of the galaxy than the other? Here, this is brighter than the other if you fit a line. That's what you're supposed to see here. Here they're brighter, here they're fainter. And here, when you plot the distribution of aurolari stars and you fit it, you hardly see much of a barred signature. It'd be a very weak bar, if anything. And it's the same number of stars. The only difference is the reddening that is used.
Are the light curves good enough to use the aurolaris themselves?
So for minimum light, so there are not as many epochs in the infrared as there are for OGLE. So OGLE, you probably could, even though not all stars have that good, they all have really good I band light curves, but V bands not as good, and you need both those pass bands. And in the VDV, I think again they have more epochs in the K band, but in that J band they don't have as many. So it would be
V minus K.
V minus K. I don't know if there is a calibration for V minus K minimum light, but that could probably be done. It could be organized. So that could be one way forward, right? Use V minus K. Yeah, that would be. So this discrepancy is still here, and I'm just not sure what I don't have to take a side. So I don't know what the answer is here. I think it illustrates the intrigue of aurolari stars and the difficulty of using aurolari stars as tracers in really highly reddened fields. We can sharpen our Swiss Army knife by doing more studies with this. So how about the velocities? How about the motions of the aurolari stars? So what's curious and what doesn't sit very well with me is that when the Gibbs team separated their stars by metal rich and metal poor, they also checked to see if there's a difference in the kinematics, and there's really very little difference in the velocities between these two populations. So you would.
Which two populations are they in?
This is the metal rich stars, and these are the metal poor stars. And the red shows the velocities of the metal rich stars, and the blue shows the velocities of the metal poor stars. They do this by a function of latitude. And there's hardly a difference between the rotation here and here. I would expect a more rounder distribution to have more chaotic orbits. Yes, Mike, are you gonna?
Yeah, sorry to interrupt, but I just hate this plot that Zocoli et al. Produced, because really, we don't see any evidence of this in BBBS. There is no great split in structure at FE over H0. There is a continuous structure, as I'll mention later. So I'm not surprised that there's no kinematic distinction, because this is just not real.
But we do see as you said, see a continuum in difference between the metal rich and the metal poor spatial distribution. And so what do the velocities show? So our approach is to look at the motions of our Lyrae stars in the inner galaxy. This is a map of the ogle Lyrae stars in the inner galaxy. And we targeted our Lyrae stars in these fields shown here. And our Lyrae stars move up and down, as everyone keeps saying. And so here you can see their motion up and down, and we have multiple epochs, not that many because it's expensive, but multiple epochs, and we fit this light curve, and we can get radial velocities with a precision of about 10 kilometers per second. And what we found is that if we just, take all the radial velocities of the Lyrae stars and we find their velocities as a function of longitude, we see the rotation is not as extreme and it has a very high velocity dispersion. However, this is probably not the best approach to use because in the inner galaxy, there is the galactic halo. So all of the stellar populations overlap in the inner galaxy, and especially when you get to the metal poor regime, -1, -1.5, there will be a more significant halo contribution. And if you don't take this into account, you're not really probing the bulge, you're probing the bulge plus the halo plus, whatever else is in there. We have proper motions now from Gaia, so we can determine orbits. We have to assume some potential, but we can at least do this, see how the stars are moving. Pericenter is the closest approach, apocenter is the furthest approach, Zmax is height above the plane. And we can, in this way, separate the halo and the bulge. We define halo as stars that have an apocenter of larger than 4.5 kiloparsecs. So they're not confined within the bulge. They're going all over the galaxy. We call that a halo. And bulge stars, we say, okay, their orbits are confined within 3.54 kiloparsecs of the inner galaxy. And what we find is that the halo stars are really driving this large velocity dispersion. Once you remove those stars, the velocity dispersion becomes very similar to what we saw in the giants and the red clump stars. The halo maybe has a little bit, I don't know what is going on with this rotation. Maybe it's a little bit rotating. The bulge Lyrae stars, those still are not rotating as strongly as the younger red clump stars and giants, the more metal rich stars that we saw previously. But cleaning for the halo, I think, is really important. Here is the photometric metallicity distribution of the halo and the bulge. And you see the halo is a little bit more metal poor than the bulge, what we would expect. And we're hoping on improving the metallicities, the photometric metallicities, at least finding better than photometric metallicities of the Lyrae stars in the center part of the galaxy. This is another paper that came out in 2020, and this is a cool result because they use proper motions to determine the velocity, the rotation curve without radial velocities of the galaxy. And they find, similar to our results, that the Lyrae stars are rotating slower and have a large velocity dispersion. But without that radial velocity component, without three-dimensional velocities, you cannot take out the halo contributions. So this is based on a factor of 10 times more than our survey, but there is for sure still a halo in it. And I want to point out, this is a table of the calculation of halo contamination from different surveys. Our paper, we found 25% of our Lyrae stars, a fourth, 1 in every 4 are in the halo. The paper I showed before estimate only 5 to 7% are in the halo, which is why they didn't think they had a clean for the halo. Petrovitsky et al. In 2020 also found about a fourth to a third are halo, and other metal poor surveys are also finding about half of these metal poor stars are in the halo. So I would say don't always trust results where the halo is not cleaned from these metal poor stars. So we're trying to also look at stars that are maybe, you know, the oldest signatures of a merger, and those would be located in the most central part with the tightest orbits from different simulations of stars. So stars on the tightest orbits and in the center of the galaxy are thought to be the oldest kinds of stars. Oops, wrong way. And so what we did is I separated our sample by stars with the tightest orbits and stars with not as tight orbits, but still confined to the bulge. And we do maybe see some kind of a difference in their velocities as well as their velocity dispersion, suggesting that maybe the stars with the tightest orbits are potentially part of this classical type bulge. Wrong way again. Okay, but remember, we are really doing some selection here. So these are the stars with the tightest orbits. They're confined to this region, but they could be moving like this. And this is the stars, the kind of stars with less tight orbits. And we see a difference in the spatial distribution between the Aurora Lyrae stars that are in this region. They kind of trace out the bar, and those that are, you know, have the tightest orbits, which kind of look more flat in distance. How about the metallicities? So this is what we were looking at. We wanted to increase our sample of stars with tight orbits. So we have to go closer to the plane where there's more likely that you'll find a star in a tight orbit. And we got new spectra of Aurora Lyrae stars in this field. And we used the calcium triplet line to measure their velocities as well as their abundances. George Wallerstein showed that there was a relation between calcium triplet and Fe/H. This relation has since been improved by Zdeněk Prudl, who is one of my collaborators on this project. And I'm not going to give that relation. I'm going to give the Wallerstein relation. If you want it, I'm sure he will share it with you. It's a lot of work that went into his calibration of the calcium triplet to metallicity. And now I can show you our results for metallicity. We first find that the metallicity of the Aurora Lyrae stars does not change as you go in galactic latitude. So here we split these our stars up by latitude, and we don't see a real difference in metallicity. This is in contrast to the red clump in the giant stars, but of course we're only probing these this metal pore component. So maybe it's not a surprise that there's not a real gradient. Instead, we find a difference in metallicity if we split by apocenter. So the stars with the tightest orbits, shown in pink, tend to have higher metallicities than those with greater apodistances. And here's a scatter plot to show this. These are our best abundances that we're showing. We see this trend right here, which could suggest that stars with the tightest orbits also have different chemical abundances than those in the bulge, but with not as tight of orbits. So my last slide, conclusions. Is there a classical bulge in the Milky Way galaxy? Is our bulge bimodal? We don't know yet, but I think Aurora Lyrae stars as old stars can offer clues. Within an old Aurora Lyrae sample, we think that there may be two different old populations in the bulge, one that traces the bar and one that does not. Only the stars on the tightest orbit are the ones that seem to not trace the bar. The Aurora Lyrae stars that are not as tightly bound seem to follow the massive bar-like structure that dominates the light in the disk today. So thank you.
We have questions. Yes, we do. Okay.
Sort of a comment more than a question, but isn't it just semantics whether it's the inner halo that formed first? You got the early accretion, hierarchical formation, as to later accretion, so that, the inner halo, not only are they orbits of halo stars that have to pass quite close, but they're also the earliest accretion events. But secondly, isn't it possible the way you get to be most tightly bound is through dissipation, losing energy, and it's possible that those most tightly bound stars actually formed in the inner disk?
Yeah, so definitely the semantics for what is the bulge, what is the inner halo, is something that the community is grappling with, right? How do you define a bulge? So generally how we define a bulge is, a central concentration of stars that poofs out. So we could call everything, we don't just call it, right, the disk and the halo. So we do have this bulge. So what is it? Is there a large component of an inner halo? Yeah, I don't know.
Just one more comment.
Yes.
the blue horizontal branch stars don't show any rotation. They're classical halo. In the classical.
But why do you suggest the inner disk? That's because these stars are so never.
No, I'm not talking about those. I was talking about the ones here that go from -1 to -1.5. There's most tightly bound ones on the early disk. Gas.
Yeah, so these would probably be the oldest stars, right?
Oldest ones that may be formed in situ.
Yeah, they may be formed in situ. Yeah. So I mean, that's what we're trying to figure out, right? So how was what was the makeup of all these stars in the center? Yeah.
So one more question in the audience.
Actually, it's more of like a comment that the difference between whether they are following the bar or not following the bar between the different photometric studies like Dekany et al. And Petrukovic et al. Can be almost completely explained by calculating the extinction wrong, especially in the Petrukovic et al. Case, because they use the Nataf et al. Formula that has both optical and near-infrared color in the calculation, but that is based on the VISTA variables in the Via Lactea survey photometry, where they didn't calibrate the photometric 0 points correctly in the most dense parts of the bulge. And I have earned a few mortal enemies about this in Cambridge because I pointed out that they are just wrong. So yeah, we can talk about this later.
Yeah, so my comment about that is if you get something wrong, you generally don't see a trend that matches, you know, the line of cloud inclination that we see for the bar. So it's kind of funny that they got it wrong exactly like they should to see you know the bar. So
no. The problem is that because Nataf used the wrong data to calibrate his extinction relation, and then that gets used by the OGO team. So that's the problem.
yeah, so we will see. This plot does not use the Nataf relation. The Vives Aurelari stars does not use the Nataf relation. They use the Wessenheit magnitudes. I'm not taking a side, I don't really know, but this does not use the Nataf relation. This uses Wessenheit magnitudes. Yeah.
You know, I just don't see the trend that that line shows.
This was published in 2020 too. This was just published last year, so,
Yeah.
or this year, I guess.
Do you see it?
Well, we did a least square, so we repeated this. This is our data. And yeah, if you fit a line, this is what, you know, this is the line that's showed.
Very sensitive.
Yeah. So we haven't done a weighted least squares. So that could be something we do. I wanted to reproduce their paper. So this is published, you know, and I wanted to see if I could reproduce this. And it's pretty straightforward to reproduce it. But I wonder if you did a weighted least squares, because there definitely are errors in the distances.
Hard way to make it look
You know.
Okay, so.
But I want to look into this more. I think it's really an interesting.
Okay, so we're cutting into lunch. So let's thank Andrea and all the speakers.